All right, so let's try to pick up where we left off. One thing I want to remind all of you, I hate this, but a lot of the doctor appointments I have are scheduled so far in advance. I don't know what my schedule is going to be like. So the next one I have is this Thursday at 1 o'clock. There's no way I can get that. In fact, the last time I was in the waiting room till 2 o'clock. So there's no way I can get back in time. So Tuesday, what I want you to do instead is, for you that have not finished up all your simulations for the lab, I want you to finish that up. I noticed that everybody took off real quick Friday when you heard that I probably wasn't going to be here. Like, hey, day off. What I meant was for you guys to stay here. I was here up until 2 o'clock. I would have stayed if any of you needed my help in doing the simulations. But I heard no, everybody took off, so I said, okay, I will too. Uh, anyhow, so anyway, work on those simulations. Have you all finished all of them? Because before you come into the lab Friday, I'm going to want to see that you've done them. Okay, because you need those simulations to say, to figure out if you're getting the right answers. Okay, it's going to be a way to go in there and say, yes, I do have this one set up. I think it's an OR gate and it's working as an OR gate. You don't want to go in there and be taking the wrong data, and then when you go to write the lab up, you find out your data is all mixed up, and then you got to really try to do something. And I can usually tell if what you're trying to do is um, fix something where it was screwed up in the lab. So anyhow, finish that on Thursday, and I'll see you here on Friday. I'm sorry. Not at all. I won't. I don't even know if I'll be here uh, earlier in the day. I mean, to me, I don't have any classes before that, and I don't see a lot of reason to come down here and then turn around and go all the way back up there. Uh, Keep in mind, if you guys need help, email me. If I really have to come down here, most of the time, I'll do it. I won't do it all the time because I'll have something like a doctor's appointment set up, so I won't do it. But most of the time, I will. All right, so let's try to pick up where we left off the other day, and I believe it was somewhere right around here, and we were starting to talk about the fan out and CMOS. And fan out, or for CMOS chips, it's more of a capacitive load, and so we're not concerned so much about how many uh, gates this thing can drive as far as current goes, because the only time there's current is what? When it's changing states. So these have very low power, and they're great for applications, that use a battery of some sort. If you use TTL in your phones today, you'd be putting them in or plugging them in about every half hour to charge them up again. It would be using so much power. So what happens here is this adds a capacitive load, and what that does is, the best diagram I've ever had is right here. It slows things down a little bit, so we'll still get from our 0 to 5 volts, whatever it needs to be. In TTL, when you have an overload, the voltage level doesn't even get up to what it's supposed to be, so you have a logic problem. Here, it's not a logic problem, it's a timing problem. And timing, I'll tell you what, good luck finding a timing problem. They are the hardest thing to troubleshoot. The other thing that's really hard to troubleshoot, remember earlier in this class and a couple of sets of slides, and I do mean it, good engineers are also good troubleshooters, because you're never going to come up with a design the first time, or rarely are you going to come up with a design the first time that's going to work. So you have to be able to figure out what's wrong with this and go in and fix it. So good engineers also have to be good troubleshooters, and timing is very difficult to find a problem with. The other one is when you have more than one problem and you're only expecting one, and you got two or three problems, then you can imagine how difficult that would get. Okay, so this jumps into a whole new topic. It's still fan out, but now we're looking at different families of TTL devices, and like this one might be a standard 7400, and this one might be an ALS 7400. How many can it drive? Now you want to be real careful. I think logically you can understand this, but we got to look at these formulas a little bit. You have to look at both the output when the output's low and when the output's high, or the input's low and the input's high, to make sure, it should be output, to make sure that you have the right number of gates and that you don't exceed how many it can drive. The reason you have to test both, and this is when we're hooking up a bunch of ICs and not necessarily when you're working with programmable chips. But if you're hooking up a couple of different programmable chips, now you got to start thinking about it again. But here, we got the formulas for fan out high and fan out low. And what we have to do is figure out, is there enough current to drive the number of gates that we have? And if the low, let's say, was 20, but the high, we found that it could only drive 5, in a digital circuit, are you going to have some high and some low values? Or are they always going to be low or always going to be high? Well, they're going to be switching, right? So you choose whichever one is the worst case. If the high said that all you can drive are 5 gates, I don't care if the low says you can drive 500. You better only hook up 5 gates there, or you're going to hit a situation where you overload that driving gate and end up not getting the correct values. So here we've got, the question is how many 7400. Now here I'm talking, if you see 7400 or 74XX, I'm just talking about how many in that series. So it could be a 7400, 7432, 7408. It's just something with 74, not 74 ALS 32 or 74 something or other. Okay, it's the 7400 series. So it could be AND gates, NAND gates, it could be anything here. But for this one, we got lucky. If you go all the way back to that other sheet, let me see if I can do this. I don't know if I can. I don't think I can have 2 versions of this up at one time. Let me try doing it this way. I'll call up our Moodle website and I'll pull up that TTL. Have any of you started trying to do that homework? It's kind of rough, isn't it? It is. It's rough. And I don't know if you've noticed, but I went in there for some of y'all and I saw that your homework, why isn't that going to? Why? So I won't ever find it. Well, here it's acting like they've got 2 of them up. Let's get rid of that. Maybe this one. Shoot. Okay, this one should work now. It's not. Is it Moodle to? There it is. That's what I'm looking for. I went into your homework, and when I was looking at some of the grades, it was like, okay, on these first ones, I know you guys don't always know what it is I'm talking about or the way that these have been worded. So what I did was went in and saw if you did it twice and one of your scores was like 4 and the next one was 10, I went, okay, I'm guessing the 4 meant that you didn't understand the way the questions were worded. And when you got the answers, you went, oh, I see now, and went and did it again and did a 10. So I went in there and I started deleting those low scores. Okay, so you wouldn't have an average. That average would have given you what? 4 and a 10. And, thank you. Yeah, I know how to do that. I was testing y'all. Yeah, you guys believe that crap, don't you? Okay, I'm going to be able to flip back and forth to this slide so that we can look at these. So remember I told you at home, when you're doing these, the best thing you can do is lay a ruler or something down. Okay, so let's go here. And here we're looking at the 7400 series, and I said what I found there for output low minimum was 16 milliamps, and the input low maximum, the maximum it can see and still see a low, is 1.6 milliamps. The negative sign just means that the current is coming out of the chip instead of going into the chip. Okay, remember all currents are defined as going in. So if we look at, I want to see where I got those values. Here's a 7400 series. Input low, it is a max, negative 1.6 milliamps. Output low, a positive 16 milliamps. So that is going into the chip. Now, a lot of people, that's where they start having a problem. It's like, wait, what do you mean? You've got an output value, but the current's flowing into the chip. But it is, and I thought I showed some of that and how that worked the other day. If you have a problem with it, we can still talk about it. But we get 16 divided by 1.6, and on our slides it shows us that's going to equal 10. I don't have any units here because this is milliamps and this is milliamps. So what's the units there? There really aren't any, are there? What I've put out here in some of the stuff I've worked with, I've just called it unit loads. Okay, a unit load. It just means if I have a 7400 chip that's like a NAND gate or something, that output can be tied to 10 other inputs. And then if you went further than that, if you put 11 inputs out there, it just wouldn't work. Okay, or you can't be sure it'll always work. It probably would. When you get up to 12, 13, 14, now you know it's not going to work. But at 11, it'll probably work. It's just how much do you want to chance that? Now we got to look at the output. We looked at the input, so we look at output. Or I'm sorry, the high values. The input high is a max of 0.04 milliamps, and the output high is 0.4. Make sure you get those values right. And then when you see those, it should show you 10 again. So this one's good. No matter what, you can hook 10 gates up. If you hooked up any more, it's a good possibility it's not going to work. Any questions on that? Okay, so here's where it's starting to get a little bit of trouble, mixing families. Now, it should have been in your first digital classes, they should have been asking just standard gates. Okay, now we're asking where we start mixing things up. And it might be that we have a 74 ALS, a 7400, a 74 LS, and they're all being driven by a 74S. Will that work? Okay, and then you just add up the currents. You can't go back here and if you have one of each of them, Well, then you go here and add this current to this current to this current or whatever it is, and add them up and divide it by the other, see if it'll work. Okay, here we're making it simpler and saying how many 74 ALS 100 TTL inputs can be driven by a single 7400. Now watch the way that those questions are being worded. Remember that your homework, this is worth 1 whole point. So if you get an 80, it's like you get 0.8 points instead of 1. There's not a big difference. But if you really aren't understanding the way I'm wording them, you can email me and ask questions, and it won't take much to ask me to get rid of your earlier attempts at this. Okay, so let's go on here. The ALS, we got to look these up again. Now, if it's driving, it says how many of these can be driven by. So these are the ones we're looking at. They're going to be driven by something else. So these are inputs. The ALS are inputs in this case, and the 7400 are outputs. So we're looking for input high, and I usually, what I do is take out that ruler, write down these values, and I write these 4 values down this way before I ever try to do this. Otherwise, I mess it up. Now, again, if you don't care that it's not that much of a in point values, that's okay. So 7400, I'm sorry, I messed that up. We're looking for, let's see, it's being driven by this, so we're looking for the output here. Output low, output minimum for 7400. Output low and output high. So 7400, output high is 0.4. I'm going to write that down. And poor guys at home, write it down, but it's 0.4 milliamps for I output high. And I output low is what? 16 milliamps. Is that right? Output low and output high. These are the ones for, if it's the one driving, then we're only concerned with its outputs. Now, this one, we're looking for the inputs for the 74 ALS, because that one's being driven by this 7400 chip. So let's go look at the input low and input high for the ALS 100. So here's ALS, here's input low and input high, 0.1 and 0.02. So input high is what? 0.02, and I input low is 0.1. And we don't have to really worry about the positive or negative signs. Again, those are just there to tell us the direction of the current. If the direction's important, you'll work on that. So it looks like I put the right values in. 16 divided by 0.1 says 160. If our output was always going to be low, we could drive 160 inputs, 74 ALS 100. But our output's not always going to be low. Sometimes it's going to be high. And when it's high, we can only drive 20. So we've always got to choose the worst case there. So the question would be like this on a test or on these homeworks. And believe me, if you're seeing them on the homeworks, you're going to see them on the midterm. So how many 7400 or ALS 100 series inputs can be driven by a single 7400 series output? The answer is 20. It's the worst case there. Okay. Now, we got to look a little bit further than this too. Logic levels must be compatible also. So the output low max and the input low max here, the input low max has to be greater than or equal to the output low max, and the output high minimum must be greater than or equal to the input minimum. So, and we look at these currents. This was kind of reducing those first few pages for fan out. It's just IOL minimum must be greater than or equal to I input low max, and the output high min is greater than the I input high max. Okay, so that fan out must not be exceeded at all. Okay, so let's look here. These are some other time definitions. We're going to talk about propagation delays. Propagation delay is typically the time between an event happening on the input of a device before the output changes. Okay, the output might not change, so to really measure it, you got to see one of those times when it does change. It's measured from the 50% mark of the input of that gate to the 50% mark of the output of that gate. Okay, so in this case, our propagation delay is right here from this point to this point. So this is an input went from a high to a low, and we're expecting the output now to go from low to high. When it's 50% of that high value going to high, those are the places we mark, and it's propagation delay. Okay, then we look at rise time and low time, or fall time. Rise time is the time it takes. Why they say 10% and 90%, I don't know, but it's always been a standard. The time it takes to go from 10% of its maximum voltage or current or whatever to 90% of its highest value. And fall time is from 90% down to 10%. Okay, so some of these we need to know. Now we look at some of these different families that are out there, and I'm not going to go through all this. Some of these are really old. They're going to be high power dissipation. We're going to look at ECL. They've still got high power dissipation. We're going to look at these. I would guess that most of you have never heard of that, because I had never heard of that. And it's still really high power dissipation, and we can't use that. Everything nowadays digital, almost everything digital is battery driven, so we want as low power as we can get. The metal oxide semiconductor and the complementary metal oxide semiconductor are going to have very low power dissipation, and that's what we want. Now it says it's a little slow, but when you start to think about it, we don't have to have things running on a phone, let's say, or something like that, a digital camera. It doesn't have to be running super, gigabytes fast or gigahertz fast for a person that's using it. We'll still be able to see it. Now, if it starts to get real slow, you start getting annoyed with it, right? So if your computer's turning on and it's taking forever and taking forever, it wouldn't be the CMOS problem. It would be something else. We know that on the computers. It's too much is being loaded up. Too much crap is on the computer. But on other devices, if it's getting too slow, it could be that it's what was that? We care about this. If it's too slow, we've got too much going on there. Most of us, for our phones and stuff like that, it's not going to be too slow. So, and these advanced type CMOS technology, if we can get those, that would be great, because they got faster propagation delays. So they also have fairly good power dissipation. Okay, now taking another topic, and what I should do in these is put a page that says now we're going to a new topic, instead of just giving y'all whiplash and moving from one to another. here we're looking at a typical uh, TTL type totem pole output. This is uh, we've seen these. I hope you've seen these before. Uh, this is I've seen these pretty much, and we're looking at the we need an input driving the top one, and input driving the bottom one to get our output the way it's supposed to be. Now, sometimes we're going to see these with open collectors or in the CMOS uh, world in open drains. Now, here is a symbol that we use for output low logic level. The lower transistor here must be saturated, and for the output high, then we've got to get this top one saturated and this one open for this to happen. Okay, so then we get something like this, and our output, we're going to say this one here then is driving, this first one is driving the second one. So the current has got to be flowing this way, right? If this one's high, because this looks like an open circuit, current's got to flow this way. So we've got to look at some of these resistor values. Are some of you getting there in the homework where you're looking at resistor values or not? Not yet? Okay, when you get there, just take it real easy. You're probably gonna need more than 2 attempts. Okay, so here, what is the current through the lower transistor in the first stage? Well, it's got to be the whole 16 milliamps that's going through here. What happens here if you've got these all set up and both of them are providing 16 milliamps, we got 32 milliamps going through there. There's something weird going on there. What's going on there that looks weird to you? Anything? Or can you not tell because I've just got lines, resistors, and switches? It looks like we've got one that's supposed to be an output driving these two that are inputs. That could be okay. But it could also be that we've got two here that are outputs tied together to drive this input. Now that we just can't do, can we? Okay. Chances are when you have open collector outputs, you might run into the situation where you have two outputs tied together. Okay. And it shouldn't be something that you run into very often because most times you're going to run into programmable chips. But if you run into something where you have two outputs tied together, if you don't want to see the smoke come out of those chips, then they're going to have to be open collector. Okay, so here we're looking at the third one. Here we're looking at this one driving both of these. There's nothing wrong with that. But if this had 16 milliamps and this one had 16 milliamps, then this thing better be able to take 32 milliamps coming out or coming into it. Okay, so add a third one, we get 48. We're starting to have a lot of currents going here. So those excessive currents could damage those circuits. So we have something called, this is where we're connecting some outputs together. That circuit should look really weird. You never see, 3 AND gates with the outputs tied together. Okay, but this one is actually called, if you have something like this, and a low on any single gate output. So in this case, a low on any input would cause a low on that output, and it would drive all of those gates low. Okay, but in the process of doing that, if we didn't have it set up right where they're open collector and the right resistor values, then we start seeing a lot of smoke, and that's not fun. Okay, so here we're going to use NAND gate to combine these outputs together. That's one way to settle that. Another solution, so that's the first one. We take those 4 AND gates and disconnect this, and we have them tied out here, and we use an AND gate here to combine those outputs. Another one is using open collector circuits. So when we do that, they're specifically designed to drive that single line with several device outputs. So here, okay, it provides capability to switch currents up to 16 milliamps or actually higher with flexible voltage supply values. So let's take a little bit of a look at this. Here is a typical output. We have an output here that doesn't have a resistor that would pull it high. So this output can't ever go high unless we have something pulling it up to 5 volts. If we had an input high voltage here, it would turn this transistor on, so we would have a high voltage here, and it would turn this one on, so that would make it look like a short circuit, but it would just be looking at ground. We would never see anything going high. So these open collector circuits are real useful for this kind of stuff, anything that's requiring some higher currents. Okay, let's take a look at this now. Here's a possible circuit. Any gate in this whole circuit here, any one of those transistors can pull the output line low. So we're saying that the output is right here. Okay, right here. It's any one of these can pull it low. If this one had an input voltage that pulled this saturated, it would pull this output to ground. Whether all of these had no input voltage, so it looked like all open circuits, would still have this one that would short it to ground. So we have to look at how much current could be going through here and make sure that we have a resistor, because this is going to be on the output. We have to decide what resistor goes there and make sure this circuit still works without tearing everything up. Okay, so let's look at this a little bit. And like I told you the other day, when I was a student here, most students just reached in and pulled out a 1K and said this should work. And most of the time it did. Okay, but it was because they were lucky, not because they knew what they were doing. Okay, so here, if RP, if this pull-up resistor is too small, okay, then the currents through the open collector circuits will be too large. That's these. Okay, and the circuit could be damaged. If RP is too large, then there's insufficient current, and we won't be able to get the right voltage level here. So we've got to get an RP value that's right. Okay, so let's look at how we're going to figure that out. So the first thing we need to do is look at the minimum RP value, and that happens when all the open collector circuits are in their high state. Okay. Now, did I do that right? Okay. So to determine, this is not working right. There it is. To determine RP, we've got to look at, we're looking at the minimum RP when all those exist. So the first thing we look at is N1, the number of open collector circuits. Here we've got 4, right? And N2 is the number of driven circuits. Now these are going to be in some formulas I'm about to give you. So that's why it's real important to know which one's which. So N1 is the number of open collector circuits. That's these 4. And 2 is the number of driven gates or input circuits, and that's 2 in this case. Then the current that's going to flow through this pull-up resistor is going to, now think about this. This should make some sense to you. If it doesn't, this is where we need to stop and look at it. N1 times the current for when this output is high. So whatever we've got here, if this output's high, then we need to know what those currents would be. Now I know I've got them all driven as, or all drawn as output currents. Wait a minute. This would be with the output high. This current would be coming down this way anyhow. Okay. Then N2 is, we've got 2 gates here, and what is required for its input current, for a high input current. So we go back and we get these values off this thing again. Output low, input high, output low, output high, all that. We got to go back to that. And then we got to look at the number of gates and see what we're coming up with here. So this particular formula, okay, we're going to rearrange it a little bit so that we can get RP. And RP, did I say max or minimum? This is minimum RP. And then it looked like I went to maximum RP max. We've got VCC, that's just 5 volts, minus V input high. Okay, the input here is high. So what's the input for these? Let's say these are 7400. What would be that input voltage? V input high. There's standard TTL. V input high is minimum is 2 volts, right? So we've got that. So we've got VCC minus that 2 volts is about 3 volts. Okay. Now we take N1 times the number of output high here. If that output high current is 250 microamps or 0.25 milliamps, we got 4 times that, or 1 milliamp. And N2 times input high, here if the input high is 50 microamps, we 2 times that and we get another milliamp, so we should have 2 milliamps there. And add that all up and do the division. Somehow I got 1100. Is that right? 1100 microamps? That's 100. Let's say it is. Yeah, it looks like it is. Okay, 3 divided by that is 2.73. Okay, so we got to remember that value or write it down somewhere. Our RP max is 2.73 kilo ohms.
You just kept it micro instead of going to.
I'm sorry?
You just kept it in micro instead of just going to billion. It could have just been 1.1 million instead of the 1100 micro.
Okay.
Well, you were saying it should be 1. It should be 1.
Yeah, I think that's right, because this would be this would be 1,000, and that would be okay.
You were just saying 1 milliamp and then 0.1 million.
Sometimes my brain don't function, so that's right. This looks good. 2.73. Now we've got to look at when RP is a minimum, and here we got, we don't have to go through all this every time. We get to these formulas, and we go through this. Did I do that again? Well, I was probably in a hurry trying to get these done, and who knows what I was doing. I was trying to get them done though. So here we're saying the maximum RP current is when, and be careful what I'm saying there, is when I output low in any single output collector or open collector output. Okay. And that open collector output must be able to sync both IRP and N2, so this current here and these 2 currents here added up. Okay, now we got to rearrange this to get RP. and we end up with, okay, first thing I did was I subtracted this from both sides and got IRP equals this, and then did some division and got this formula. Hopefully they are right, because I don't know how many times I think somebody would tell me in class, that's wrong. And I'd go, really? And they would convince me it was wrong. And then I would go in and I would fix it. And then later I would look at it and go, that wasn't wrong. They were wrong. So why am I second guessing me? And then I would put it back. And so who knows if I've got all of these right. I think I finally do, because there was a lot of time where it was back and forth, and I think I finally got them all right. And so we can go with these. So here, if we have output low is 20 milliamps, and over here the input low is 2 or minus 2 milliamps, right? That's 20. This is 2. We've got 2 of these gates, so this would be 4 milliamps. We got a whole actual value of 24 milliamps here. VCC is still 5 volts. What's VIL max? Input low. V input low. It should be the same for all these. It should be about 0.8 volts, right? So V input low is about 0.8 volts. Now, so we've got 5 minus 0.8 or 4.2 divided by this 24 milliamps. Or I'm sorry, look, this is minus. So we've got 16 milliamps, right? And we get 262.5 ohms, not kiloohms. So RP minimum is, according to what I got there, 262.5 ohms. Okay? So which one are we going to use? Well, the best thing to do is look at those, and you really could choose just about any value in between them, not just, not completely, but the best thing to do is average them. And here we got 1.494 ohms as the average. Okay, so we got about 1,500 ohms. Starting to see that 1K looks like it would work, right? It is between the 262 and the 27 ohms. So then the other thing that we have to do now is, okay, we do this. I'm going to go over here to web pages. I don't think that's the one I want, but I'm going to look at that. That's this. I thought I was doing this. I exited out. Why would I do that? Who knows why I'm doing the things I do. UNCC.edu. If I left it for a second, it'd probably show me my, nope, it's not going to do it. Slash, great, that's nice. Okay, SJCI. I can get this far without having to go any further. I'll hit enter and go to the digital systems, and then go down to the bottom of the page, and here I've got standard resistor and capacitor values. So I think I've said in most of those homework problems, find the closest standard resistor value. We got in our answer here, I didn't write it down. What was it? It's hard to see, but about 1.5K. So do we have anything here that's at 1.5K? We sure do. So I wouldn't use 1.4. I wouldn't get a rheostat and adjust it to 1,494 ohms. I wouldn't do that. You can if you want, you know, but I wouldn't do that. I would use the 50 or 1.5K, and we're probably done. Now, but still, I think you can see why if those students had chose a 1K resistor, would it work? It probably would work. So did they get lucky? Sure they did. But they didn't have to do all those calculations where they could have messed up. Okay. So I've got on one of these pages, page 90 out of 100, I've got all those formulas. They should be right. If you look through these and you think you found something wrong, you're welcome to tell me, but now you're going to have to convince me. Okay? And I'm not going to easily second guess myself again. I've gone through this plenty of times in the last 13 years. Okay, so here, for this particular circuit, it's a little bit different. We got 20 milliamps, and IOH is 250 microamps, and we got input low is minus 2 milliamps, and the 50 microamps, it looks like those values all stay the same. I want to know what RP is. And then we got V input low and V input high for the gates that are out there as 0.5 volts and 2.7 volts. So using those values, what does RP have to be? And I've gone through here, and for the first set here, it's VCC minus this, and then N1. How many N1s, or what's N1? Well, IOH is 250 microamps, but what is N1? 2? So we got 2. I got 2 big switches showing up there. So this is another place where a lot of mistakes can be made. Sorry about the way that's drawn, but I do have 2. It would be nicer, you're right, if this is pulled over here and this looked more like they were outputs, but they're still working. N2 is the number of these, and we've got 3, so it's 3 times this 50 microamps, and we get those values, and got 3.5K basically. Okay, now RP minimum, I put that one down here so I wouldn't lose it. Now see here, see this? This is a little indication that at one point somebody told me I was wrong, because there was a minus sign there. And so I put a plus sign here. And then when I found out I was right, I went back and fixed it again to minus sign. It's just this is one of those areas where they convinced me for a little while. It's funny how somebody that really talks like they know what they're doing, they can really, and they're really, they're just so sure of themselves, they can talk me into it. Anyhow, so we've got IOL, 20 milliamps. That's all by itself. It doesn't matter that there's 2. It's just that particular current. And IL is the number of these times that. So we've got 3 times the 2 milliamps, and we get this. Okay. Now, I think where some of the questioning came in was, is this minus? Since this is minus, or is it minus a negative so that this turns out to be plus? Just leave it the negative current. Okay, it's like we add them up, but it's a negative current, and just leave it there. Okay, so 5 minus 0.5, 20 milliamps minus 6 milliamps. we should get this, and that's 321 ohms. We take the average of those two, and we get about 2K. 1K is between these, so it'll probably work. So if you're one of those that go pull 1K out of the bench, it's probably going to work. All right? But you should, to make it work the best it should, you should probably pull out 2,000. Now, where are you going to see this? This semester, there's probably only one place that you'll see that, maybe two. One of them is on those quizzes for homework, and the other place is on a test. I don't think you're going to walk into the lab and have to calculate all this for open collectors. Okay? This is purely academic. Okay, so that gets us out of here. We did all these things, looked at some basic gates, looked at positive and negative logic values, and looked at a few other things. Okay, let's close that out. We still got a little bit of time. I know we don't have much. What I'm going to do here is just kind of talk about where we're going. It'll be next week, right? So if, where did that go? Why did it do it that way? So if we're looking at the logic functions optimization and hazard protection, well, what do I mean by those? The logic function optimization should be pretty clear. We're looking at some string of values or expressions, and we've got to decide, do we want to have a sum of products formula, or do we want a product of sum?
What is it noise?
I don't know, but I'm just glad I can't hear very well, because it would hearing that, sometimes it drives me crazy. I think I'm the only one that these are picking up some weird radio station or something like that. Sometimes I think, it's yeah. I start doing this, and you can hear that, can't you? I did that once, and to a group of students, and I thought, God, you've got to have seen some old man with hearing aids before. And they just ring and ring and ring. And I looked at this group and I said, wait a minute, I got to contact the mothership. And there were people in that class that went, what's he doing? It's like, just leave me alone a minute. Yeah, they're saying do that homework. These poor people were freaking out. You never know. Okay, logic function optimization is trying to get things down to the simplest function, and we can use Boolean algebra, or we can look at entering these variables on Carnot maps. We're going to see which value or which way we like the best and look at it. There are a couple other ways that we're not used to looking at. One is call up multisim and put this expression in multisim. It's got a logic converter in there, or a logic simplifier. The thing is, you gotta enter the values kind of weird. You've got to put in there, like for a not, let's say it was A and not B, you would have to put in A, and I don't believe you have to put a star in there for anding them, but then you put a B and then a single quote, and the single quote saying not B. Okay, now that's a little weird, but once you learn how the syntax goes for those, then you should be able to do it without a problem. The other way to do this, and none of you will ever have to do this with Xilinx, and we're going to use Xilinx a lot. But in Xilinx, you just put in the expression. I don't care how big and long it is, put it in. And Xilinx will always reduce it to the simplest formula for you. Okay? Do we really care about it? No. we just got to make sure that our input formula is correct. Okay, and when we got that, let Xilinx do its work and everything will be fine. Okay, so we're going to look at 2 and 3 variable Carnot maps. You may not have seen them turned over this way, but you may not have seen A up here and B over here, but that's the way I like to do them. If you really want me to do them the other way, I can do them, but I won't be able to just like that come up with these for the distance ed class, so you'll just have to get used to some of these. The 4x4 Carnot map. The one that I'm not showing here is I'm not showing when we have a 5x5 or a 5x4. Now what do we do? What if we have 5 input variables? Well, it could be three-dimensional. You can do that. Another way to do it is to enter in that 4 variable K-map, enter some of the variables in there. It's called a variable entered map. So if you had A, B, C, and D, you could put D in the map, zeros, ones, and Ds, and be able to figure it out that way. Much, much easier than starting to look at 3 or 4 dimensional maps. Anyway, so we'll look at some of them. We'll review some of the Boolean, and then we'll go on from there. Now, when it said this, eliminate hazards and sources of hazards, I'm going to show you in there where there's sometimes where we can see it basically best on a Carnot map, but you can see where there's going to be a race to the end. Okay, who's going to get there first? One of them is going to be high and one's going to be low. Who's going to get to the end first to make that switch? So we're going to end up with glitches, either a glitch that goes low or a glitch that goes high. And we got to find out what's the best way to eliminate those. So it's much better to have a circuit that's correct all the time, right, where we eliminate those glitches, than have one that's got the fewest number of variables or the fewest number of terms. That might not be the best thing to have. We might want to have the no hazards, no spikes or anything in our circuit. Okay, so we'll pick up with that Tuesday. Thursday, again, I won't be here. So you guys got plenty of things to do until then. And I will see you a week from today. And I'm going to hit stop for the distance ed students, and we're done. Almost 1 full hour. It should have been an hour and 15 minutes, but that'll never